Again, connectivity issue, I think.
Lakshman?
मनीष
थोड़ा एक सेकंड लक्ष्मण को फोन कीजिए मनीष।
या पीछे छोड़ देना।
I think sir, after presentation we can read the biodata of Professor Bartwal sir.
Just a minute, just a minute. Just a minute.
Problem of connectivity with Lakshman.
I'm really sorry, sir. There's a network issue here, so I'm really sorry for inconvenience.
I was thinking it is from my part. It is not from my part. It is from your part. Okay.
Yes, I really apologize for that. Should I again give a brief introduction?
Sure, sure.
Okay, sir. So before I inviting Professor K.S. Bartwal, sir, I would like to give a brief introduction of him to all of you. Sir has done his MSc in physics from HEMVATI GARHWAL University, Srinagar, GARHWAL, and then PhD in physics from Banaras Hindu University, Varanasi. His area of interest was solid state physics, condensed matter physics, laser physics, and nanomaterial physics. From 1990 to 1993, Sir has worked as scientist in National Physical Laboratory, New Delhi, and from 1993 to 2019, Sir has worked as scientist in the Department of Atomic Energy at Raja Ramanna Center for Advanced Technology, Indore. Sir is also member of different scientific societies like Indian Laser Association, Indian Physics Association, Indian Association for Crystal Growth, and Materials Research Society of India. Sir is also editorial board member of many international journals like Advance in Material Science USA, Universal J of Material Science USA, Open Journal of Modern Physics USA, and Journal of Applied Physics ISST India. Sir has also published more than 250 papers in different international journals. So it's really a huge honor for all of us, sir, to having you in this virtual conference. So with this brief introduction, I would like to invite Dr. K.S. Bartwal, sir, for his keynote address. Dr. Bartwal, sir, over to you, sir.
You can see my slides now. मेरी slides दिखती हैं?
Yes sir, yes sir.
Yes, sir.
Please continue.
Slides देख रहे हैं? Okay, fine.
Yes, sir.
Okay, but I cannot see them. I must see first and then. I must see first.
It's visible, but I think you need to make it full screen mode.
Okay, this is what it is
Yes,
now.
yes.
And now you can
Yes,
see.
now. Yes, fine.
Fine. Thank you so much. Very, very good morning to all of you. And this is really a privilege and pleasure to be part of this e-conference at GARHWAL University and the Government College Dehradun. I'm thankful to the organizers and giving me this opportunity, and particularly the authorities in the seminar, Professor Nautial, the convener of the seminar, Dr. Manish Unyal, the secretary of the seminar. And then finally, I would like to thank the university authorities. I think Madam Vice Chancellor is not there. Then Professor Dimri, the Dean of Sciences in my university. Professor Upadhyay, the HOD Physics, Department of Physics there. Professor Bhatt sir, the coordinator of the seminar. He is also my colleague, friend, and classmate, I think. And Dr. Pamar, I saw there, and so many other friends we had been there during that period of time when I studied there. It has always been a pleasure to be part of the seminar at HEMVATI NANDAN University there, because I feel like homecoming every time when I participate there. And then it is always a homecoming because most of the time it is a physical conference there. So physically I go there, and then I go to Gopeshwar to see my mother, to see my brothers and sisters there. I still feel like going there, but this time it was not happening. I was supposed to come physically up to Dehradun, but somehow it has to be postponed due to this corona crisis. But okay, fine. We are there. We are not physically, then at least online we can talk to each other and see each other and all that. Now coming to the main business of the day, the seminar is basically on recent advances in material science. And this topic is really very relevant, not only today, but historically. The material science is so important, as Professor Dimri has also told about something. Then I find that there is a recent development in material science is nanomaterials. So I thought I'll be talking about the nanomaterials. A lot of people will be talking about the materials in general. So I thought I'll be talking about nanomaterials. So I chose my topic of nanomaterials in this particular seminar. And but before going directly to my talk, 1 or 2 slides I'll be showing on the recent development in materials and why materials are so important. Why materials are important for our society, as well as for the betterment of the society, as well as for the development of the nation in general. Okay, so before going to the nanomaterials, I'll be talking about 2-3 slides on general materials. So this is what it is. Why materials? Why materials are so important? As people have talked about, and we know that metals have played an important role in our civilization. Everybody knows that. And entire eras have been named after those materials, particularly those materials which are developed or procured during that period of time. Those eras has been named after those materials, as I have shown in this slide, that we have the Stone Age, we have the Bronze Age, Iron Age, Polymer Age, Concrete Age, Silicon Age, and now the Information Age. And this is all the development of materials, systematic development of materials with time. And if you read this, if you see that early on people use only natural materials. Previously, very early days, particularly the Stone Age and the Bronze Age and all that, people use only materials which are available in the nature, like stone, clay, skin, wood. But today, if you say precisely, the synthetic materials have taken a lead. Synthetic materials means the man-made materials, which are developed and developed in the laboratories or in the institutions. So they have taken the lead. And if you see from our household to the space, see our households, kitchenwares, utensils, drawing room luxuries, clothes, car, mobile, and whatnot, everything is made of materials. So these materials are basically the synthetic materials. So that's why I told you that the materials have played an important role in our civilization. For the development of any kind of thing, we need materials. And for those materials, we need a lot of research on those materials, how to develop them, how to procure them, and how to make them useful for that particular application we need them. So from our kitchen to our space, we need a materials. So that's why material science is such an important area. And it is not only a science, material science is only one subject. It is a combination of physics, chemistry, math, engineering, and everything come together. And then only you can develop a material for your application. So this is what the importance of the material nowadays. And that's why I told I will take few slides, two or three slides, to show the importance of the material and the development of those materials for our particular application. For example, we see that from Stone Age, at the time of Stone Age, everything is made of stone, whether it is a weapon, whether it is a jewelry, whether it is a utensil, everything is made of stone. Then we involvement, then the fire. The fire was found sometimes after the Stone Age. Then it changes everything, because once you have a fire, you can really go for the metals which are available that time in the nature. So many things can be made out of those metals. Then today CNT, carbon nanotube. If you see the development in the material science from the Stone Age to the CNT today, the CNT is 100 times, 1,000 times lesser than the thickness of a human hair. So this can be developed, this can be made, and this can be used nowadays. Then steel plane, you see this, there are so many materials used for this plane so that it is invisible. So some coating of special materials, coating of special paints is done on these material pins and body so that it is invisible. And today we have reached up to the structure of DNA. So this is the information is basically, so DNA structure we understand today. And if you see that, once you understand the DNA structure, you understand so many things about your life. And for example, nowadays, if you see this COVID-19 vaccine, it has been developed within less than a year time. And it has happened just because we understand the DNA. Though COVID-19 virus is not DNA based, it is RNA based, but it is almost the same. DNA or RNA, it is almost the same. If you understand DNA and RNA, that was the reason that within 10 months time, the vaccine has been developed for COVID-19. So this is just because of our understanding of DNA molecule or RNA molecule. So the science has progressed, the material science has progressed a lot from Stone Age to the DNA structure today. So I have given only 4 or 5 examples, but you can quote many examples that where we reached, we have progressed a lot. And today, if you see that, if you read these lines, if you look at the most developed nation or the economy in the world today, the best material processing production capabilities, those countries which have those things, they are called the developed nation or the economically very high economic developed countries. So if you have best metals processing and production capabilities, you are the developed nation. You are economically very ahead. So these are the things. So materials development and design and production capabilities are must for the development of a nation today. So I have just given these 2 slides just for the sake of flavor of materials, what is material and why it is so important for our day-to-day life and for the betterment of the society, betterment of the nation, and betterment of the humankind. So now coming down to the classification of materials. So I have given you a little bit flavor of material science and its importance. Now coming down to the classification of materials. On the atomic order basis, on the basis of atomic order, you can classify the materials. So we have 4 kinds of materials, monatomic gases, where there is no order. Because I will be talking only about on the basis of atomic order. Monatomic gases, there is no atomic order. So atoms are randomly arranged together. For example, the argon gas. Then we have a amorphous materials, a long range order, only short range order, long range order, but in a very small scale, there is short range order. For example, the amorphous silicon, the glasses, the plastics. Then we have a liquid crystal, short range order, but a long range order in a very small volume. For example, liquid crystal display polymers, and so many polymers which are used for liquid crystal displays today. And then the 4th is the crystalline materials. Crystalline materials are very important because they have both short as well as the long range order. So you can have short range order for your application, you require them, you can use that. If you need a long range order, you can use that portion. So crystalline in both the volumes, the small volume with the short range, large volume with the long range. So you can use crystalline materials. So they have 2 categories, the single crystal, so long range, the polycrystal, very small range. For example, you have a silicon, solar cells and all that. So many kind of single crystals are used for solar cell development, optical devices and other devices where you require a long range order. So you use single crystals. But where you require single short range order, in a short volume, your work is done, then you go for the polycrystalline material, like alloys, metals, and most ceramics. They are polycrystalline materials, but they have a short range order. Up to a limited volume, up to a limited length, they have a structure there, single crystal structure sort of thing. And then the new class of materials are nanomaterials. This is what I will be talking about. So on the basis of atomic order, this is a crystalline material, but having very small size. Nanomaterials are the materials where you have a unit cell, but with a very, very small size. Few units of few atoms or few molecules have the atomic order, but at the same time, it is not like a single crystal. It is not like a huge structure with so many atomic distances, so many crystalline distances. Unit cell is maybe 1, maybe 2, maybe 3 at the most. So this will give the single crystal structure, but at the same time, it will not give a long range order. Sorry. Now, that was the brief introduction of material and then the classification of the materials. Now coming to the main topic, my topic is nanomaterials. So nanomaterials finally come down to the nanotechnology. I have given one slide, what is the nanotechnology? Thinking big, working small. What does it mean? Thinking big means these nanotechnologies today, using those nanomaterials, nanotechnology is a huge importance in our life, day-to-day life. So that's why I written it, thinking big, because you have to think big to get the technology. And the working is small, because your working area is very small. You are working in the nano area. And basically you are working within say 1 and 100 nanometers. So working very small, but thinking very big. So this is just a, what is nano then? What is the definition of nano? Nano derives from the Greek word nanos, which means dwarf or extremely small. So this is a Greek word, basically comes from the nanos. And 1 nanometer is basically a millionth of a meter, means 10 to the minus 9 of a meter. So where we will be talking or where we will be working with, we will be working in this scale, 10 to the minus 9 of a meter. So nanoscale involves a range from approximately 100 nanometer down to 1 nanometer. So this is the scale. Here onwards, I'll be talking about the nanotechnology or the nanomaterials or the nanodevices. All will fall in this range. If it is 100 nanometer down to 1 nanometer, below 1 nanometer, very difficult to control, to use. Above 100 nanometer, it is in 0.1 micron. So it is difficult to have those characteristics in that range because it is a micron, sub-micron range. So those properties which we require as a nanomaterial for that particular device, it will not work in that area. So we will be talking only about the scale 100 nanometer down to 1 nanometer. So this is the window. This is a window for the nanometer devices where we are in 1 nanometer to 100 nanometer range. So for the sake of just to visualize how it looks like, what will be a size, that nano sizes, manipulating material at the atomic and molecular scale. You have to manipulate the material within this range. So if you see this, if you see a child of about 1 meter length, then minus 9 of a meter is C63 molecule and plus 9 of a meter is moon orbit. So this is the visualization of the scale. If you want to visualize which scale we are talking about, 10 to the plus 9 of a meter, 10 to the minus 9 of a meter, and then compare with the human child of a meter or so. So this is where we are. So we will be talking about this length, 10 to the minus 9 of a meter, means one carbon 60 molecule is of the order of 1 nanometer. So this is 1 billionth of a meter. So what we have to understand is the structure of these materials, those materials which are of this scale. So they have novel properties. They have physical and chemical and biological properties which are different than their bulk properties. If they are in bulk size, the properties are a little bit different than their nano size properties. So what is our ultimate goal then? Our ultimate goal is to build these structures, to build those devices or those materials essentially from scratch by atom by atom. Atom by atom, you have to make those devices to use for your application within that range. That range is 1 to 100 nanometer. So again, one scale, just to visualize the scale, a billionth of a nanometer, a full length human being. Then one dot on the nail is of the size of 1 million of a nanometer. Then thousands of nanometer, a biological cell. Then few nanometers is a DNA molecule, 2.5 nanometer or so. And this less than a nanometer is an individual atom. So this is just the scale, how this goes from a billion of nanometer to 1 nanometer, or 1 nanometer to a billion of nanometer. So what we will be talking about, we'll be talking about in this range somewhere here, 1 nanometer to 100 nanometer, where we can really work with, and we can derive or develop our devices or useful application of those materials in this range. So nanoscale has already been our routine. So it is not that we don't know this nanoscale. We don't know the things which are in nano size. Our air contaminants, our water contaminants, they all fall in these categories. You see, from 1 nanometer to 100 micron, we have so many contaminants which are always present in our air and water as a contaminant, and we are using to remove them. We are using machines, so we are using something like our RO systems and filtration systems and all that. So we are removing them, but at the same time, what I mean to say is, we know the scale, we are using those scale, those sizes to remove them. But for last 20 years, we have been using these scales for our development of materials, for development of devices in this scale range. So this is not very new also. So Feynman has told long back during 1959, he has told that there's plenty of space. He has told that we will have very small miniaturization of the devices. At that time, nanometer scale was not there. At that time, nanometers had not been developed. But he has predicted that we can write an Encyclopedia Britannica, 24 volume of that in a head of a pin. Means in a micron size pinhead, we can write this much information, 24 volumes of Encyclopedia Britannica. What was that? That was basically miniaturization. And that miniaturization is possible today. This was required patterning at 10 nanometer scale, but at that time it was not possible at all. It was not even thinkable also at that time. But it has happened today. I will give you an example where it come from. It has come from this IC chip started from this PN junction. I'm not going into detail. This is a very common thing. This is the main thing, the Moore's law. Moore's law is basically, it is basically a number of integrated transistors on a integrated circuit. In one chip, how many transistors you can put that it can have this much speed, capacity, sensor capacity, speed, memory, and all that. It depends all because of on an integrated chip, how many transistors you can put. So it has started somewhere here. And then today we have 100,000, 1 billion, 1 million transistors on a chip. But this is the old story. If you see the new story today we have 5 billion transistors that can be placed in a chip. That is called 7 nanometer node chip development. And it is for last almost a year. It has been in the market. But just 1 week back, on 6th May, maybe 1 week back, 2021, IBM announced the 2 millimeter chip technology they have developed, in which 50 million transistor on a fingernail size chip, which is called the nano seed chip, has been developed. So they have announced on 6th May 2021 the 2 millimeter chip technology, in which 50 billion transistors on a fingernail chipset can be put. So now the speed of the transistor, the speed of that particular technology will be tremendous. It will be 75% more speed, and the energy consumption will be less than 40%. So this is what is the new development. Just 1 week back, they have announced this. I'll give you one example of this. USB flash drive, everybody is keeping that in the pocket. Like it was in MB, now it is available even in 8 GB to 2 terabit size. A small size USB, you can have this many data, and you can allow that for 100,000 write and erase cycles, and the age is of 10 to 100 years of age. So this has come just because of this miniaturization of the technology, the development of those chipsets where you can put millions of transistors in one chip. So this is small volume, this is small size of pocket size, not even pocket, it is a finger size USB drive have this 2 TB data you can put, and in future it will be maybe 20 TB you can have. So this is just one example I gave. Nanotechnology is so cool. So physics wise, if you take example of gold, the melting point of gold is this and color is golden. That's why it is called gold. But if the size changes, if the size of molecule of gold changes from 1 nanometer, 20 nanometer, 100 nanometer, the melting point changes, the color changes, and if it is sub nanometer, it will be black. So you cannot imagine that it is a gold, chemically it is a gold, but the color is black just because of the size. So where that color is coming from? The color is coming from basically those particle size, which is less than a sub nanometer or the nanometer, very small particle size. So the physics changes, the transition changes. I will show you in the next slide. So how the color is changes just because the transmission and those intra-band transitions changes just because of the size of the particles. You see the cadmium selenide, same thing happens. If you see this 3 nanometer, 4 nano, 5 nano, 6 nano, 7 nano, the color is different. It is just absorption. So this transition, the excitation energy levels, they produce these colors simply, and that excitation means the transition from one band to another band is different for the different size of the particles. So that's why they look in different colors. So this is the basic physics behind this optical absorption, where from the electron is coming and where it is going to be absorbed. So that particular band is the absorption band, and that absorption band gives the color to that material. So that's why we see a different color with a different size of the material, whether it is a gold, whether it is a cadmium selenide, or in some cases, whether it is a silver as well. So this is basically an optical absorption of the particle size with a different size range. Nanotechnology is not a very new phenomenon. As back as 4th century AD, so there was a lacquerous cup, so made of some metals, and then it was basically coated with a colloidal solution of silver and gold. They were not knowing what they are doing, but they did it. So if you see this in reflected light, it will look green, but when it is a transmitted light, now it is red. Where from this color came? The people were not knowing that time, because they have just put the silver, colloidal silver and gold nanoparticles solution on this to make it beautiful. Nothing more than that. But it has come today when the people have done electron microscopy, particularly the SEM, scanning electron microscopy of those surface of that lacquerous cup. They found that they have the gold and silver nanoparticles on the surface, which gives this reflected light color green and transmitted light color red, just because of these nanoparticles of gold and silver. So this is what is the phenomenon behind that, but they were not knowing it. They had just made, to make that beautiful, they have put the colloidal silver and gold solution on the surface of this cup. Some application of, Thank you. Some application of nanotechnology, bulk material application. I will just give few slides for application, then I will come down to the material. Passive nanomaterials, for example, titanium dioxide in sunscreen, in food packaging, disinfect food applications. Silver nanoparticles, again, carbon nanotubes for stain-resistant textiles. In some textiles, it is being used so that there will be no stain and no dust cannot go in the textiles. Cerium oxide as a fuel catalyst is very fast catalyst. Nanoscale additives or surface treatments of fabrics can make them resist wrinkles, staining, and bacterial growth. So these some of the, and particularly this here, it is these additives are basically mainly titanium dioxide and sometimes silver oxides. Some of them can be used as a thin films on the eyeglasses, computer and camera displays, windows, make them water and residue repellent, anti-reflective, self-cleaning, resistance to ultraviolet or infrared light, anti-fog, antimicrobial, scratch resistance or electrically conductive. So some of the nanomaterials are being regularly used for films and eyeglasses. Then lightweight weighing of cars, truck, airplanes, boats, and aircraft would lead to a significant fuel saving, because nowadays carbon nano fibers, carbon nanotubes, and these carbon based materials are being used for these vehicles or airplanes and spacecrafts, where they are very lightweight, they are very strength-wise, they are very good, and they reduce the fuel consumption of the device or the machine. Nanostructure ceramics coatings exhibit greater toughness. So if you have the nanostructured ceramic materials, compared to the bulk ceramic, they are very, very tough. They are very strong mechanically. So these are in routine use, like aluminum oxide. So L2O3 is very strong material, but at the same time, you have nanostructure powder of aluminum oxide. So this is much more tougher than the normal aluminum oxide. Some application in the medical side. So nanoparticles are being extensively investigated for biomedical application, including tissue engineering, drug delivery, and biosensors. I'll give a little bit later, I'll give you CNT, example of CNT. So for the drug delivery system or the biosensor systems, we use carbon nanotubes. Then delivering drug directly to the cell by using nanoparticles or nanotubes, particular nanoparticles, to deliver drugs to a cancerous cell. So suppose we have a cancerous cell in some area of the body. So if you give full medicine, the whole body can be affected. But if you have a nanotube, you can just directly put the drug molecule directly to that particular cell using carbon nanotube. So this cancerous cell can be dissolved there, can be killed there, and the remaining cell will be unaffected. So some sort of those things, those techniques are called the drug delivery systems. Another one is the bismuth nanoparticles to concentrate the radiation. So if one is going for the radiation therapy, so to concentrate radiation therapy in that particular area, bismuth nanoparticles were given, so that the total radiation is remain in that particular area, so the tumor only, the cancer tumor only will be affected by that radiation, and the remaining part will be unaffected. So deliver a cardiac stem cell to damage heart tissues. In heart, is some part of heart, those stem cells, the damaged stem cell can be directly repaired by using some of the nanoparticles directly put in that particular area, and the remaining portion of the heart will be unaffected. Similarly, insulin and enzymes can be given together, so that if the body requires insulin, it will provide insulin. Body requires enzyme, it will provide enzyme. So it directly put in the body in a particular place where you can have both insulin and enzyme together as per the requirement. In some cases, kill bacteria in the body by just gold nanoparticles. and infrared light in that particular area. So the whole body is not getting affected. Nanorobots could be programmed to repair a specific disease cell similar to the antibodies. So you can have those robotic nanoparticles can be put in the body in a particular area, particular cell. Only those will be active, the remaining will be inactive. In some cases, skin creams, all that is being made of these nanomaterials. Now, so that was the basic of basic concepts of nanomaterials, what they are, how they are procured, how they are used, and what particular use of those nanomaterials are there in the society today, whether it is a engineering use, whether it is a scientific use, whether it is a medical use. Now, how to make them. So next few slides, I'll be talking about those nanomaterials, how to procure them, how to make them, how to discuss them, and then finally put them for application. So this is a three-way basically. Synthesize the material, and make to characterize them, make for application. Or you have a particular material for particular application, you want the material, then for that application, what property there should be and how to synthesize that. So vice versa, you can have the from your application point of view, you develop the material. From the developed material, you can go for the application, search for the application, which application it will be much useful. So this is what the basic fundamental of how to make them. So synthesis of nanomaterials, there are two approaches. One is top down, another is bottom up. Top down is basically, suppose this is a nanomaterial you want to make. So you have a block material of that material. So top down is basically a monolithic processing at a nanoscale. Means you just press that and crush that in the nano size, or you have a nanomaterial from atom to atom or molecule, systematically assemble them in the form of nanomaterials. So we have a top down process as well as the bottom up process. So you can make by both the ways these nanomaterials as per your application. So at least one dimension is between 1 nanometer. So what material we are talking about? I have told you earlier. So we are talking the material in 1 nanometer to 100 nanometer range. So they can be 2D structures, 1D structures, or 0D structures. Means 2-dimensional, 1-dimensional, and 0-dimensional. So in 2-dimensional, we can have thin films, planar quantum wells, superlattices, 1-dimensional nanowires, quantum wires, nanorods, and nanotubes. And 0 dimensions, you have nanoparticles and the quantum dots. So these are basically the materials in these 3 different dimensions. You can use them for your application as per your requirement. So size dependent properties, I've told that size dependent properties are very important for these molecules, as I've shown in the case of silver and cadmium selenide and gold, that the size changes. A lot of physical, chemical, and biological property of the material changes. So main properties, the physical properties are basically thermal properties, mechanical properties, optical properties, electrical properties, magnetic properties. They change drastically when we have a size different from the bulk size. So whether it is 1 nanometer or 100 nanometer and in micron size, so these properties will change drastically. And according to change in those properties, according to your application, you can choose the material for that particular application. 3 reasons why these properties are different, why they show these different properties. First is the quantization of energy states, that is the confinement, quantum confinement. This is what is called quantum confinement, because the energy states changes with the size. Then the structural effect, we have the grain boundaries, we have high interactive volumes, so it will change the grain boundary length, so it will change the mechanical property of the material. Then the critical length scale. The critical length scale is basically 1 nanometer down to 100 nanometer. So this length scale, the property will be different compared to the bulk as well as the sub-nanometer scale. So these 3 reasons are there why these properties of these nanomaterials are different. For example, I will take a surface to volume ratio. This is one of the important things. When we have a nanoscale, so 10% surface atoms are there when it is a nano. But at the same time, when it is a bulk, it has only 0.3% surface atoms. What does it mean? It means on surface, in nano case, 10% atoms are at the surface. That's why it is very, very active material. But at the same time, when same material, same silicon is in bulk, only 0.03% atoms are at the surface. So the activity of this material is compared to this material is almost 300 times more. So this is the reason surface to volume ratio is one of the important factor why these nanomaterials are so active compared to the bulk material of the same chemical species. Where did it come from? It comes from the band diagram at the nanoscale. How band diagram changes at the nanoscale. If you see that 3-dimensional band diagram, 2-dimensional, 1-dimensional, and 0-dimensional. So how band diagram changes, the energy band changes. So this is where it is. So it is in quantum case when there is a 0 dimension, there is only discrete energy levels. Where we have a continuous energy at bulk, but in 0 dimension, it is discreteness. And this discreteness is increasing by changing the dimensions. So 3D, 2D, then 1D, and then complete discreteness in 0 dimensions. Now, I'll give 2-3 examples of the material which we have developed in our laboratory here in RRCAT, so that you can feel that how these nanoparticles are made. So particularly, I have taken example of lithium niobate nanoparticles, and both the techniques I have used here, I'll show you the top down as well as the bottom up. Top down is basically we have taken, suppose we have taken a lithium niobate single crystal or polycrystalline bulk, and across that with the high energy ball mill, cast that in a high energy ball mill, so it become a nano size lithium niobate. Similarly, when we start from the niobate or carbonate or sometimes any other salt, and then use this chemical reaction, the citrate gel method, and finally we have a nanoparticles of lithium niobate. So starting from carbonates or hydroxides or something, and then entering into getting the nanoparticles of lithium niobate. This is the bottom up. This bottom up means starting from the atom, lithium atom, niobium atom, then getting the lithium niobate. And here we have the bulk lithium niobate, and then getting the size, downing the size of the particle from micron to nano. So this is the top down, this is the bottom up technique. I'm not going into detail of these things because this is not the forum to talk about all these. So this is pure and single phase, nearly stoichiometric lithium niobate nanoparticles, getting from that both the techniques. You will get powder only. So this technique or that technique, you will have the nano particles in size ranging from 30 to 40, 50 nanometers. And then those particles, those nanoparticles can be used in some matrix so that we can have this type of composites used for any device. So instead of single crystals of lithium niobate, we can have now these nanocomposites, and they will work as single crystals of lithium niobate work in many of the devices. Some of the optical devices, it may not work because when there is 90+ transparency is required, then this will not work. But when you have 80% or 70% transparency is okay. For example, some of the electro-optic applications, you don't require 100% transparency or the 90% transparency. Here it will work. And it will be much cheaper than making single crystals of lithium niobate. So those, once you have made this material, so you have to check that it is stoichiometric or not, it is lithium niobate or not, it is a single structure or not, it is having those latest parameters or not. So you go for the X-rays and all that. Then finally you tell that, okay, this is the lithium niobate, this is the size, this is the particle size, and then only you can go for any application of that material. Then you have to have transmission electron microscopy of those developed materials also, because you have to have single crystal, single phase. If it is a single crystal, fine. It should have a single phase also, because if you have a different phase in one bulk, so it will not work. In some cases it will work, in some portion it will not work. So you have to check that whether it is single crystal, single phase, and certainly with the same lattice parameter in bulk from one area to another, it should have same lattice parameters. So you have to have the electron microscopy, the transmission electron microscopy, as well as the DLS size. You have to have size of those particles where the size falls. So it comes from this, I think it is 30 to 60 nanometer. It is much below than the 100 nanometer. So any device, if you have a size 1 nanometer to 100 nanometer in between, so you can develop a device from, you can use that material for a device application. And optical parameters, you can see where it falls. Basically, this shift in blue shift tells that how band gap is shifting, so where it can be useful. So for a particular application, particularly when you are using that material for optical devices, you need these information that whether it will be useful or not. Otherwise, you have to have change the size. So if you have a 30 nanometer size, it may not give in this range. So you have to change the size to 20 nanometer or 60 nanometer or something. Sometimes it is 100 nanometer, very near to the boundary. So it can be useful for that particular application. So for optical, electro-optic application and optical application, you need to have the non-band gap of that material, particularly leaf and avid. The band gap should be much stable with the size. Then another example is YAG, that is yttrium aluminum garnet, which is very good laser material by which you can make the solid-state laser. So this is made in our laboratory. This has been made in 30 to 50 nanometer size and at a very low temperature, only 850 degrees Celsius. The melting point of this material is around 2000 degrees Celsius. However, by using this technique, glycol method, it has been made at the temperature of 850 degrees Celsius. So this is one of the beautiful technique for making these type of materials, particularly the high melting point material at very low temperature. So only 800 and 950 degrees Celsius you can get these YAG nanoparticles using the nitrates or sometimes or carbonates of that particular material, and using this glycol route you can get this nanoparticles, these nanoparticles. And again, we go for this XRD DEX and techniques for making sure that it is a single phase, it is a single crystal, and it is a in a whole area, it is a single phase material. Then scanning electron microscopy doing same thing. Then the transmission electron microscopy again for knowing the structure as well as the size of the particles, as well as the it is size supposed to be 25 to 50 nanometer, well enough to make any device out of it and use for in some cases when you make we make devices out of these nanomaterials, it work like it is a single crystal of YAG. High resolution for getting the atomic size and atomic unit cell of that material. Then preparation of carbon nanotubes. In some cases, carbon nanotubes, as I have told you, for that delivery system, this is one of the important material nowadays. And not only that, for that delivery system, but it is a very high strength material. And nowadays, some textiles are being made using this carbon nanotubes when it is a multiple volume or when it is a multiple wall carbon nanotubes. Single wall is used for the delivery system. Multiple wall can be used for strength material with a high strength. So these multiple wall carbon nanotubes are very good for making bigger mechanical structures. So again, this technique is basically chemical vapor deposition technique, and it is a thermal chemical vapor deposition technique. Means you are using a thermal shot by source is using acetylene gas. So with the help of hydrogen gas and a thermal shot, you are getting carbon from this. So this carbon, that by breaking this acetylene gas, you get the carbon nanotubes. So this is where you have the pattern. You are getting these peaks. Yes, it is a carbon nanotube. So this looks like this. So if you see the scanning electron microscopy picture of these carbon nanotubes made of this CVD technique, so you have these many carbon nanotubes coming in one shot. So within say a few minutes, you can have number of carbon nanotubes made by CVD technique using this acetylene gas as a source material. So these are the high resolution, and you see that this much length. This is a very single wall tube, and this can be used for a delivery system. This is a multiple wall tube. You can have multiple wall there. So this can be used for another application. So for this, you have to see the structure there. How much, if there is anything other than carbon, you will have a different diffraction pattern there. So you have to have a single phase. You have to have only carbon, no graphite. If there is a graphite, then it's going to be less, very, very less compared to the carbon. So you have to check those, characterize those materials. Once you have made the material like this, so you have to check them, whether it is a single phase, whether it is a single crystal, whether it is a, in the bulk, it is only one material. Chemical, it is only carbon. It should not be graphite. Now I have almost finished that example of three materials. When I have took the example of lead and arabate, then the yard, and now the carbon nanotube, then the potential risk of, I'm almost finishing my talk now. So potential risk of nanotechnology. There are a lot of risks with the nanotechnologies today. Nanoparticles is a health issue. It's a big issue. Nanoparticles could be inhaled, swallowed, absorbed through skin, or deliberately injected. This is very, very harmful because you cannot see them. It's very small. You cannot taste them because it's tasteless. So it can be inhaled by mistake. It can be swallowed. It can be absorbed through skin, or deliberately injected into the body, and it is very, very harmful. So could they be, and there will be very, very less symptoms. You can directly see that it is just because of the nanoparticle of that particular material. So this is one of the potential risk of these nanomaterials. Then environmental nanoparticles could accumulate in soil, water, plant, or traditional filters are too big to catch them. If it is accumulated in soil, water, or plants, it is very difficult to remove them because all the filters, the traditional filters, are too big to catch them because they are very small. They can pass, they can cross any sort of filters. And then the new risk assessment method should be needed to take the so
hello, sir.
National and international agencies are beginning to study the risk, and they are thinking to just how to stop that too. Now, this is the journey where we started in supposed to be 2000 to 2020, where we have reached today the passive nanostructure, the active nanostructure, systems of nanosystems, and then the molecular nanosystems today. So we have progressed a lot during last 20 years in nanotechnology, and many more than this because some of the things have not been put here. But at the same time, as I told you, these are very extraordinary important materials. They are very useful materials, but at the same time, they are very risky too. So as I have given an example, the potential risk of those materials, the potential use of those materials, but at the same time, we have to have the balance between the potential risk and potential technology development of those materials. So these are the main things. And then finally, the summary of my talk is the field of nanotechnology offers possibility of transforming the materials application. It has really transformed the material science, and it integrates physics, chemistry, biology, metal engineering, and earth sciences. All the sciences are being integrated by the nanotechnology, and the structure and property changes with size distribution of the particles. It has the understanding of this is must to use these materials for your application. And it is possible to design materials for a specific application by just manipulating the size, and shape of the material you have developed for a particular application, and then the application of these materials in medicine, automobiles, food, textile, cosmetics, and whatnot. Everywhere you can use them. Only thing is you must understand the material. And I will just want to share one example that the so many COVID-19 vaccines are coming in the market and are already there in the market, but a nanomaterial based vaccine is about to come, and one of the Indian company is working on this with the American companies, and within next say 2-3 months it is in the third phase of trial now. So that will be on the basic principle of the nano size particles of those vaccine materials, and that will be much more useful, I think, because as I have told, the surface to volume ratio, these are very active materials. So just because of the surface to volume ratio, the number of atoms on the surface, it will be very, very active. So you require less medicine, you will require less medicine for a particular application. So I think it will be coming in next few months time. There will be another version of COVID-19 vaccine based on the nanoparticles. And I think, thank you very much. Thank you so much.
Okay. Thank you, sir. Now it's a question time, and only 3 and 4 questions. Only it's a question time, and only 3 and 4 questions.
Let me come. Okay. Okay, fine.
Thank you, sir.
Okay.
Only 3 and 4 questions from the participants, research scholars, students.
Sure, I'll be happy.
Only 3 and 4 questions. If anybody have any query, students, research scholars.
Hello, sir.
Please.
Good morning. So myself, Ankit Bartwal from GARHWAL University.
Okay.
So I want to ask, what is the compulsion of FTIR in the field of nanotechnology?
Compulsion, you told, or you told compulsion, you asked?
Yes, sir.
It is not compulsion, basically. It is use. You can use that.
Yes.
You can use as a tool. It is a tool. FTIR is a tool. So this is not a compulsion. Yes. In some cases, suppose I will give one example. I'll give example of CNT, carbon nanotubes.
Yes, sir.
When I are talking about any material based on the carbon, then FTIR is must, because in particular band, which is not possible to get from your diffraction techniques like electron microscopy or neutron microscopy, neutron diffraction, or those things is not possible to get those information from these techniques. But in FTIR or Raman, you can get those information because it is a carbon based.
Yes.
So it is not a compulsion, it is a technique. So FTIR is a very good technique to know the structure of that material in that particular area. So it is a not compulsion, but it is a requirement. Some cases it is a requirement, particularly in carbon case.
Yes. Yes, sir.
Any other question?
Okay. Thank you, sir.
Okay.
Yes, sir. Yes.
Excuse me, sir.
Okay.
Excuse me, sir. I will ask you one question.
Yes, sure.
Please, what is your name? And from
My name is Bindia. My name is Bindia from Sirsa, Haryana.
Okay.
Sir, I asked you that how are you said that citrate soldier method is a bottom-up approach?
Bottom-up approach means what? Bottom-up approach is basically arranging the atom, arranging the material in atom or a molecule, from atom to atom, molecule to molecule, then coming down to the single crystal. Single crystal means the nanocrystal of that size. Bottom-up means that. Means starting from the material with atomic size to the molecular size. Or bottom, that is bottom-up, okay? And top-down is basically starting from the bulk, coming down to the nano size.
Sir, citrate soldier method is a bottom-up or top-down? I asking that.
Bottom-up.
Bottom-up.
Bottom-up. Where you start from the atom or molecule, below the size of the material you are making, then it is a bottom-up. When you are starting from the size above than that, then coming down to the size where you want to make, then it is a top-down.
Sir, one question also. Sir,
Sure.
how band gap energy is behaved when we go from nano to bulk material?
Which energy?
Band gap energy.
Okay, band gap energy. Band gap will increase. Once size is decreased, band gap will increase. क्यों? It will have the blue shift. आपका जो blue shift है, जो band gap है, वो blue shift होगा हमेशा.
Sir,
So
when
band gap will increase.
when we go from bulk to nano, then band gap is decrease or increase?
Increase because you are going in blue side. You are going in blue side. Blue shift हो रहा है.
Okay. Thank you, sir. Thank you so much, sir.
Okay.
Okay.